Maxime Ramzi from the University of Copenhagen to tell us about endomorphisms of THH.
Yeah, thanks very much for the opportunity to speak here. Yeah, I'm not 100% convinced that this is actually related to the special year, but I hope it will still be relevant for people. So yeah, I want to talk about endomorphisms of THH. So I guess I should maybe say a few words about THH first. THH is so an analog over the sphere spectrum of classical Hochschild homology. I probably will never say topological Hochschild homology because it's quite long to say. But yeah, you can think of this as something like this. And Hochschild homology, of course, is very interesting for many reasons. Classically, it's related to the Rham homology and so on. And maybe more relevant here, THH is related to TC and TC minus and so on, which are related to prismatic cohomology. So maybe it's a natural object to try and study. And you can think of it as some kind of noncommutative cohomology theory. So noncommutative cohomology theory, because unlike maybe the Rham cohomology, it's defined over arbitrary rings, which need not be commutative. And in fact, more generally, it's defined over stable categories or stable infinity categories. I might drop the infinity as well. And as for any cohomology theory, you can try to ask stuff like, what are operations on this cohomology theory? And that's sort of the type of thing I want to discuss today. Maybe a brief further motivation than just computing operations on something. I can tell you a bit about previous work that was done on this. So I think the original sort of paper studying operations on classical Hochschild homology was by Lode. I think the paper is called Operations on Hochschild homology or something, where he defines sort of some kind of lambda operations on HH relative to a base K. And he uses them to construct a filtration, for example, and get a more precise connection with the Rham cohomology in non-smooth cases. For example, over the rationals, he finds that this filtration, he constructs splits and has the Rham cohomology as a summand, even in non-smooth cases. And I guess these were further studied by a lot of people. So I wrote a few names. So I guess in the context of maybe string operations in string topology, which is maybe a bit further away, there's work by Wall-Westerland, further studied by Wall, where they study some kinds of, well, they try to study operations on THH or on HH, sorry, by studying what they call formal operations, which aren't exactly operations, but they map to operations, and the hope is that it's sort of maybe a dense subset or something, or at least it's injective on homology. And I think this was further studied in the case of commutative algebra by Klamt, who computes the actual operations on Hochschild homology of commutative algebras. Yes, and she finds a fun fact that these lambda operations or these shuffle operations of Lode, they can be infinitely summed. Yes. Okay, and maybe in a slightly different direction, I want to mention I realized actually in the past couple of days, sorry, so I didn't have time to actually think about it too hard, but there's this work of Leon Mondal that studies endomorphisms of the Rham cohomology. And they do a bunch of cool stuff over this. Once they figure out the endomorphisms, they do a bunch of cool stuff. So they compute deformations and they compute étale twists and so on. And so I would like to do that, and I haven't done. I mean, I have done it for étale twists because the answer is very easy in that case. But I haven't had the time to think about deformations more seriously. But it's something I want to think about later.
Concerning just the basics of this theory, so you have this theory for ordinary rings, but then people, like you said non-associative rings over a base, but then people looked at it for like in the stable endomorphism category and for infinity categories or differential gradient things. Also, so can you list the reference? Can you say how it was?
Well, so I guess for THH, it's I guess the earliest reference I know where it's really defined for stable categories is maybe in Bloomberg, Gepner, and Tabuada's work, where they study the universal property of K theory And I think they also define a version of THH. It's not, their definition is not optimal in the sense that it uses spectrally enriched categories as a model for stable infinity categories, but unfortunately the literature is quite sparse about actual THH of stable infinity categories. And I guess maybe the best reference is a non-existent work by Thomas Nikolaus, where he sort of in 2018 maybe announced in this Oberwaffe workshop how to define THH in a really nice way for stable categories, but it's not out yet.
Just for rings. And
For rings, yeah, they have Nikolaus.
It's like E, whatever E rings in this homotopy theory.
So for Nikolaus also do this in their paper on topological cyclic homology. They define THH for associative ring spectra. I mean, more generally, algebra objects in any sort of symmetric modular infinity category.
But there's also HSS.
There's also HS, that's true, but they don't do the cyclic mixed structure, which is, I guess, but yeah, I guess there's also, so let me give a final reference. Oiwa, Sheronske, and Sibila actually provide a much more functoriality than what's in Nikolaus Schulze, a bit less than what's in Nikolaus. Nikolaus is unexistent work, but okay. So anyway, I'll take the, well, okay. We won't need to know that much about THH to actually compute things, which is quite nice.
But will you consider THH as a cyclotron spectrum?
Not yet.
But will you?
I'll explain the kinds of things that I'll consider. So the word endomorphisms of THH can mean various different things, and I'll explain which ones I mean. So I guess I should say the point of this talk is maybe to give you a few examples of things that I can compute, but maybe more importantly, tell you how to compute them and tell you that with this method, even if you can't answer every question, at least the questions become very concrete calculations that you can make.
And did people also consider it just in a simple differential graded context?
I don't know that would make sense. I mean, yes. You can define it on differential graded categories, but then the source, if you want to compute the correct endomorphism spectrum or space, you still need some higher stuff, so it doesn't really make sense. But for example, what Bloomberg and Tabot observed is that DG things, when you localize at monoid equivalences, you get exactly like, or I guess, well, they find this in the spectral setting, but in k-linear settings, you can prove that you get exactly DG like k-linear categories. So something like this. So I mean, not to spend too much time on this, but if you do cat DG k and you invert monoid equivalences, you get k-linear stable infinity categories. So here k is maybe a discrete commutative thing. It's maybe more general even, but I don't know, at least it's good enough. Okay. Right. So this I hope I'll say about yeah. Well, anyway, right. So there's some cool direction in how you can apply this stuff, but for now I'll just stick to telling you how to compute this and some of the subtleties that show up later. Yes, and so as Lars asked, like THH has a lot of extra structure, and you can try to compute various variants of what this string of symbols could mean. So for example, the most naive version maybe is to consider THH simply as a functor on stable categories, which I'll denote by cat perf, into spectra. So that's the first variant of something I could do, and this is sort of one of the simpler answers. And it means idempotent complete. Idempotent complete stable infinity categories. Maybe you should write this infinity category of idempotent complete, but that's kind of irrelevant. Idempotent complete stable infinity categories. So you should think maybe perf R for a discrete ring, for E1 ring spectra, maybe perf X for schemes, and derived schemes and so on. But you allow all kinds of maps within those that don't necessarily come from geometry. So maybe you have push forwards and so on.
The category should be small usually.
Yes.
Or in any case, for large ones, usually it is 0 by.
Yeah, I mean, there's every small. Yeah, you can make arrangements with dualizable categories, for example, but let's say small. So that's the first variant you can consider, but THH has a lot more structure than this. So for example, you can consider THH as a spectrum with S1 action, but the answer kind of is easily deduced from this one. Maybe more interestingly, THH is a symmetric monodal functor. So you could maybe consider endomorphisms as a symmetric monodal functor. Another thing that you might care about, if you care about the Rham homology, maybe you care about k-linear things, you could ask, okay, what about endomorphisms of k-linear HH? And this still has several variants, so you could put the k-linearity here, you could put it there as well, and you could, well, one or both, and then you get different answers. But funnily enough, it turns out that even if you want to compute just the k-linear version, even for the most naive k you could think of, maybe Fp, the answer depends on on THH. So answer depends on THH in some sense. More precisely on THH. Okay. And maybe the final variant that I'll discuss, which is the one where the answer is the least, that I'm going to give you is the least complete because there's some subtleties in the integral case, is because THH has a symmetric monodal structure, whenever you plug in, I mean, you can maybe plug in algebras of a certain kind. So maybe monoidal categories, maybe symmetric monodal categories. So maybe you can do maybe a more general version involving operands, but let me just mention that this is the one that I'll discuss for concreteness. So you can do symmetric monoidal stable infinity categories. And you can put here, you can put either spectra or couch as well, but I guess this is already complicated enough. And yeah, and so here you should think more of really perfect modules over a commutative ring, maybe perfect complexes over a scheme still, but you have more complicated things like you could have genuine G-spec or compact genuine G-spectra, for example, which isn't really of this form. So these are like various variants that I'll discuss, but maybe I want to move on now to explaining how to approach these questions via like, yeah, and then show you maybe that the method applies to many different contexts, and you can then pick your favorite one.
Maxime, in the last case, what if you take commutative algebras and motives instead?
It's gonna be, well, you can do that as well. I'll explain that you can basically do, I mean, yeah, but it's different. I mean, right. Yes, and here you could also replace this by motives if you want. Okay, so maybe method. One anywhere, but okay. So what's the method? How do you compute? How do you even approach such a question? Well, the answer comes from this Bloomberg, Gebner, and Tabuada paper. So these three authors, they explain to us how to understand K-theory. I mean, I guess morally the idea goes back maybe to about 1000, but they explain to us that K-theory has some kind of universal property. And you can extend this a bit further than K-theory, so I'll state a theorem that you can deduce from there. Maybe they even state it. So I'll call them BGT. Which is that if you have A, which is a stable category and it's small enough, so it's compact. So maybe you can think of some ring of finite presentation as an E1 ring, as an associative ring. And you have E, a so-called additive invariant. So it's an invariant that satisfies the additivity theorem of Althausen, similar to K-theory. Then you can compute maps from the functor that takes the K-theory of the category of functors from A to something. So if I plug in any category here, this remains a stable category. I can take its K-theory, and this is a functor. And I can map into E. And what they explain to us is that this is exactly E evaluated at A. And I guess here, to be extremely precise, I would have to put connective K-theory. There's a version with non-connective K-theory, which is the version I'll mostly want to consider. which is that if I put non-connective K theory, then I have to assume that E is a localizing invariant, but the same thing holds. So maybe localizing non-connective. There's a small subtlety in the statement with the localizing invariant, which is that this side is not usually a localizing invariant. But the statement remains true nonetheless, even though this is no, like, even if I plug in non-connective K theory, this is not a localizing invariant in general. This is still true. And it's quite convenient to know.
Maxime,
Yeah.
Where exactly is that mapping space taken?
Yes, good question. This is a mapping space or spectrum, I guess, because I'm putting an E here. And E, I guess I should assume, has values in spectra. And this is taken in the category of functors like this. Okay. Yes. And so what does this tell us? It tells us that mapping spectrum of spaces, mapping spectra or spaces, maybe are complicated to compute in general. But if I can understand the source in terms of K theories of things, then I can maybe have a chance of computing. So you can think of this as a presentation of you have maybe some other additive invariant, maybe E0 or something, and you want to compute maps from E0 to E. Maybe E0 isn't quite of this form, but you can present it in things of this form, and then it'll give you some answers. And this is where the second ingredient comes in. Second ingredient. It's a theorem that sort of gives you such a representation for THH. So THH itself is a localizing invariant. And you know abstractly that any additive invariant will have a presentation as a co-limit of things of this form. That's for some kind of abstract reasons. But maybe you want a concrete presentation, because if you just have the abstract one, it won't really tell you anything. So yeah, the second ingredient is this a theorem of Dundas-McCarthy. That's commonly stated as THH is the linear approximation to K theory. So THH is linear approximation to K theory. So you can make this precise in really the context of good calculus. Let me maybe state a version of this, which is a bit more complicated than their result. I'll mention the connection to the result in a second. But before that, let me give you a notation. So notation. Right. So let's suppose I have C, one of those stable categories, and I have an exact functor from C to its incompletion. So how to think of this? You can think of this as some kind of bimodule. So for example, if C is of this form, so perfect complexes over R, then this is exactly the datum of an RR bimodule. Some kind of bimodule. Then I'm going to define a category of twisted endomorphisms. Well, I'm not going to define it, but I'll tell you what it is. It's the category whose objects are essentially an object of C together with its map, with a map to T of X. Okay, so of course this doesn't quite define for you an infinity category, but you can guess how the actual infinity category is defined. And the morphisms are like a morphism in the X direction plus a homotopy witnessing the square commutes. So let me just stick to this informal description for now. And let me maybe give you an example. So I told you that you should think of this as bimodules. So what does this look like in the case of actual bimodules? So if C is per R and T is maybe, let's say, sigma M tensor over R, and I'm going to make an assumption on, so example. I'm going to make an assumption here that R and M are both connective. So they're in non-negative homological degrees. Then this category of twisted endomorphisms is exactly modules of this Kreisler extension. So this is and CT is equivalent to perf R plus M. And I put sigma M here because otherwise it's not true. if I want the M over there. Okay, so you can think of this really as a categorified version of square zero extension. And the reason I'm interested in this instead of just this is that I'll want a theorem that holds for all categories and not just rings, and not just connective rings even. Yes.
So M is a bimodule.
Yes, M is a bimodule.
The R direct sum M is a ring using bimodules.
Yes, absolutely. This is the trivial square zero extension by a bimodule. Yeah, so you multiply on the left with left action, on the right with the right action, and two elements of M multiply to 0. Yes, and that makes sense even for like E1 rings and not just ordinary rings. Okay. With this notation, okay, sort of handle my boards a bit better. But with this notation, I can state a version of the Dundas-McCarthy theorem, which is the following. There's an equivalence, there's a canonical, maybe natural, well, it is certainly natural and it's also canonical. Equivalence, THH. So expressing THH of a stable infinity category in terms of a bunch of reduced K theories of these twisted endomorphism categories. So what does reduced K theory mean here? So this endomorphism category, you can see that you can, given an object, you can just remember X, forget the endomorphism, and you just have a functor to C. And conversely, if I give you an object X, I can decide to put the zeromorphism here, and that gives me a splitting. And so I can just split that off. That's reduced K theory. And this functor here is going to be functorial in the input T. And so I get this diagram that tries to ask whether it commutes with suspension. Of course, it doesn't. And so I force it to commute with suspension. So in this sense, it's a linearization of K theory. And I mean, in fact, so I stated for just C, but there's a version of THH with coefficients where if I plug in coefficients here, I can put a T here, and this is still true. And in fact, the version with coefficients is very convenient to prove the version without coefficients. Okay, let me make a remark.
The work was older than, I don't know which paper you refer to.
Yeah, this is 94.
But
Yeah, but this, the right-hand side was introduced by Christian Cassel and Goldstein.
Yes, yes. And this was conjectured by Goodwillie. I mean, Goodwillie originally conjectured that there would be a theory called THH, which would be an analog of HH, and for which this would be true.
But they didn't have the notion of stable category.
No, so that's I'm making a remark here about the relation to their work. Yeah, indeed. They didn't state it this way. They stated it specifically for C being a connective E1. I mean, in fact, they stated, so they state and prove it for only simplicial associative rings. Or simplicial rings. And then in their and connective modules, I mean simplicial modules. Simplicial bimodules. And just a bit later in there, or I don't know how, I don't know, I'm not sure about the history because it was published way later, but it was announced a bit late, just a bit later. In their work with Goodwillie for this celebrated Dundas-McCarthy theorem, so Goodwillie, they extended to connected E1 rings. E1 rings. Yes, by reducing to the simplicial case essentially, but there's a bit of a subtlety here, which is that their proof actually involves quite heavily connectivity estimates, both for K theory and for THH. And these connectivity estimates are just completely wrong. I mean, for non-connective rings and for arbitrary stable categories, which are more like non-connective rings, unlike connective rings. And so it actually takes some work to extend this to actually this version. Yeah, and by the way, so they still improve it for simplicial rings using this definition of NC, or using this fact here that I wrote. So they write it for square zero extensions. So I'm not sure actually who to attribute this fact for general categories to, because I think, so let me, okay. So you can prove it, you can actually deduce it from the connective version by using, well, the same framework of trace theories introduced by Thomas Nikolaus. So, for non-connective rings, you can use trace theories to reduce it to connective rings. In fact, you can reduce it to the sphere spectrum. To reduce to C equals perfect complexes over the sphere spectrum. That's actually enough to prove everything. And in this special case, it's actually earlier than the Dundas-McCarthy. In this special case, it's actually due to Goodwillie, as far as I know. In this case, Goodwillie, in the context of his study of A theory, and I mean, this is what motivated Goodwillie calculus in the first place.
So you're referring to Nikolaus's non-existence.
Yeah, yeah. So this is the framework of trace theories is kind of interesting. I mean, it was discovered independently in two slightly different forms by Copenhagen and for the
Maxime, isn't this non-existent thing you're referring to in Oberwolf report?
Yes, but lacking many details. Yeah, there's a report which is approximately, I think, 15 pages, and the draft that Thomas sent me is more like 70 pages. So, whether or not it's existent, I don't know.
But the idea is in those 15 pages.
All right, thank you.
So yeah, Copenhagen did a bunch of stuff about this, but it's very hard to access, and it's also not in infinity categories. It's only for ordinary categories, and it's not quite sufficient for some of these things. Honko and Schulman, they invented a notion which is the notion of shadows, and it's not exactly the same as trace theories. The difference is a bit subtle, but these were discovered essentially independently, and then Nikolaus introduced trace theories in this Oberwolf report. Oberwolf meeting, I guess. And so I don't know, this reduction or this use of trace theories, I think Thomas knew about it. And I don't know, yeah, it's been rediscovered by many people independently. So I don't know who to attribute this to, but let me, you could attribute it to Thomas, I think, probably is a good one. Yes.
So, but the theorem is true.
The theorem is true, yeah. The theorem is certainly true. In fact, it's kind of funny, for non-connective rings, where this formula here relating these twisted endomorphisms to perfect categories over the category of perfect non-places over the square zero extension, this is no longer true. The formula for the first derivative using this remains true for non-connective rings. So there's a few variants of this. It's a very robust theorem in a sense. You can do a few tweaks here and there, and it will still work. For example, for a connective ring, you can freely choose to use connective K theory or non-connective K theory, for example. Okay.
You said its equivalence in what in only as spectra or some other structure?
Well, there is other structure, but maybe let me just say as spectra. So there's an equivalence in functors from perfect categories to spectra. There is in principle much more structure. For example, you can define an a priori S1 action here, and it's the same as well. And you can also define an a priori cyclotomic structure here, and it's the same as well. Yes. But yeah, okay. And now you can start seeing how this thing I said about presentations will work out. Is that, well, I've given you THH as some kind of K theory of things. Now I just need to do a brief explanation of how it actually fits exactly in the setting, but this is not very hard. look at this formula. The point being that because I only want THH without coefficients, there's no T on the right hand side really if I remove the T, and so I can define this. I can give you an alternative description of this category of twisted endomorphisms in this special case. The point being that in that case, the map from X to sigma n X is the same thing as a map from omega n X to X. And that's the same thing as a module structure over, well, a free E1 ring on a class in degree minus n module structure. On X. So let me call this ring for now sphere brackets sigma minus n maybe. Yes, and so in conclusion, what you find from this is that endomorphisms of C twisted by sigma n is equivalent to exact functors from perfect complexes over this guy into C. And now we're exactly in this sort of setting right here. And so this allows you really to compute stuff. So let me phrase it, I guess a couple of corollaries of this. And maybe the first one, the first naive one, is just apply this formula right away and don't worry about things too much. And so you find that if E is, all right, I should say, let me just say something, let me just add a word here. I told you that for connective rings, you could freely choose between connective K and non-connective K, but for arbitrary categories, you really have to go for non-connective K theory. So for this to apply, you'll then need E to be a localizing invariant. E is a localizing invariant. Then you can give a maybe bit naive description, but it's the first description, I guess. As some kind of, well, co-Goodwillie derivative of so you can take this and run with it, and you can, for example, with this you can already compute the first variant that I mentioned, but you lose a bit of structure, and it's not. Sometimes it gets a bit more difficult to use. But let me state the second corollary, which works approximately the same, and it's more convenient for some extra structure that you might want, which is the following. If I give you two localizing invariants, then maybe up to set theory, so maybe I want to assume for this second part, I want to assume maybe that E is accessible or something, but it's kind of irrelevant. There's something you can do. You can take their day convolution.
So your localizing invariants do not preserve filtered columns?
No. Yeah. They're weakly finitary, I guess, in the sense of Langhammer, but nowadays people, I think, assume just thing. And for example, I could put TR here if I wanted, for example, which is something you might want to do. Sorry?
What did you say?
So Lars was asking whether I assume my localizing invariants to be finitary, and that is they preserve filtered colimits, and my answer was no. I don't assume that they preserve filtered colimits. In particular, one choice of E that I could choose is TR or TC. So these various like topological theories. So
What is TR?
TR is, yeah, I don't want to give you an answer.
It is compatible with sufficiently filtered with kappa filter.
Yeah, exactly. So that's what accessible means. Yeah, absolutely.
Okay.
Yeah. Yeah. So TR is going to be compatible with omega-1 filtered colimits, for example, and all of these T's as well. You can never really go beyond that. I mean, you can, more difficult. Anyway, for two localizing invariants, you can take their day convolution, which is some kind of, tensor product. So let me write this day. It's not a pointwise tensor product, because that would not be a localizing invariant anymore. And another way of using this description of THH that I gave you over there is to observe that this actually implements P1, so this first good derivative, at the level of invariance. So this is actually going to be the colimit over n of reduced E of and of blank sigma n. And this is purely formal from this description over there, just as this was purely formal from this plus the other thing. And now it's a bit more convenient because you can compute this quite often. As an example, which is the example that will be relevant for us maybe, is you can compute this, and this has been computed. I think, I don't know, the reference I know for this is Lars's paper on stable TC, but maybe, I don't know, you can tell me if this was your discovery. But this is co-chained on the circle with values in THH. There's a bit of a shift from maybe things that you might know, but this shift is accounted for by this shift between the sigma m here and the m here. So some older literature is off by a sigma with some more newer things. So maybe, yeah, maybe you're used to seeing chains on the circle, but that's accounted for by this sigma. Right. And this equivalence here now, right, equivalence is a bit more structured than you might think. So THH has an S1 action, and this S1 action matches this one. And it has a like left THH module structure, and this matches this one.
So THH is a kind of a functor on certain type of stable category with values and THH to the power S1 means the functor with sense.
It's the same functor, yeah. It's values on the category C is THH of C to the S1.
To this space of pointed maps from S1 or
Yeah, not unpointed.
unpointed maps.
Yeah, so maybe you're more used to seeing something like a function spectrum. Something like this.
Three loops, okay.
And now you can use this to answer at the same time the first two questions. So I think this one you can use to answer the first question right away, but maybe not the second one. And yes, go over there probably. Right. So how do you do this? Well, you use, I guess, in some sense, classical algebra. You use the extension and restriction of scalars adjunction. So you observe that, I don't know, maps from THH to THH. So again, this is as a functor in the functor category from stable categories to spectra. Well, this is a THH is symmetric monodal, so it's a module over itself. So I can extend scalars on this side. And this is THH linear maps. But now I just told you how to compute this. This THH to the S1. And because S1 is a finite space, I can pull this out and I get something like this. So. And now this brackets means chains rather than cochains. And this you can just evaluate to be the sphere. And so, and because you've been careful about the S1 action before, this S1 action is exactly the one you expect. So an S1 action is the same thing as an action of the spherical grouping on S1 on your thing. And so this has a canonical map to here. And the claim is that this is an equivalence. So the only endomorphisms of THH are the S1 action and the obvious linear combinations of those. So maybe in more classical terms, if you're familiar with Hochschild homology, but not so much THH, this S1 action corresponds to the Kahn differential, the Kahn operator in classical Hochschild homology, which from the perspective of the H-Carrier theorem corresponds to the Rham differential. But this is like a spherical version of that.
This is also an equivalence of E1 algebras.
Yes, it's because you have a canonical map of E1 algebras, and it's an equivalence underlying. Yes. Okay. And now, so yes, right? And so maybe before I start going on to the multiplicative version of that, let me point out that I can basically put any number of tensor products everywhere, and you get a concrete answer out. It might not look the same, but you get a concrete answer out using basic liquid calculus as well. So let me not go too much into the specific examples, but this tells you that you can basically compute everything. Okay, the multiplicative version is a bit more subtle, but not that much more. So let me explain that. I was telling people that there weren't many primes in my talk, and this is one of the points where the primes start showing up. So if you want to do the multiplicative version, so maybe symmetric monodal maps, well, this day convolution thing that I didn't tell you what it was in detail, it's supposed to encode symmetric monodal structures on functors. In particular, maps of symmetric monodal functors, they correspond exactly to commutative algebra maps for this. I mean, commutative algebra in the sense of this day convolution. And so this restriction of scalars, extension of scalars adjunction, it works just the same for commutative algebras. And so I can play the same game, except that now I'm a bit stuck because I can't just pull this S1 out. It doesn't work the same for commutative algebras, of course, but I still get something like this. So here, commutative algebras in spectra. Right, you get a description like this, and you might have a hope that this is just the circle. This is parametrized by circle. At least certainly there's a canonical map like this. But it turns out this is not so. I want to point out that the subtlety that I'm going to describe with small subtlety. The subtlety has nothing to do with THH. It's completely understood here, and it further has nothing to do with the sphere. You might be like, oh, this is higher algebra, that's complicated, but the subtlety I'm going to point out is already happens over FP. So subtlety, warning, maybe. This is not just S1. In fact, over FP, what you find is that maps of FP commutative algebras from these cochain algebras to FP, well, canonically what it is the free loop space on the P-complete circle. But maybe to be a bit more concrete, you can describe this explicitly as a core product, so this joint union, over the p-adix of a bunch of P-complete circles. So in particular, it's not even a connected space, for example.
How many?
Sorry?
How many copies?
ZP, the p-adix. The p-adix numbers, so there's like uncountably many. Many.
Depends on your model of set theory.
No, but how can you get it naturally from just doing because
The pi 0 is ZP.
The pi 0 is ZP. The higher pi, the pi 1 is also ZP at every point, and then there's no higher pi's. I could rewrite this again if you want as ZP times S1P. So I think I've told a couple of people about this. Right now, I don't really know a name for these maps. Sort of by naturality, they all reduce to either the map indexed by the number 0 or the number index or the index 1. The number 0 is the one you expect, so you just evaluate at the point. Number 1, I don't know what it is. It's just some map that's there. But it ultimately comes from Galois descent, because somehow if you go to FP bar, the subtlety goes away and you just get the P-complete circle, but by descending, you pick up a free loop space. I don't know a good name for this map. If anyone knows a good name for this map, I'd be very happy to know about it. But yeah, anyway, so it turns out that by doing some arithmetic square, this problem persists to the sphere. And so what you find is that this is something like this. A bunch of circles indexed by the profile integers. But again, I don't really know names for these maps. But yeah, but I mean, this subtlety is there and it's important, but it's unrelated to THH. Yes, and this is I should say this is due to Mendel.
Is it possible to explain what this calculation means in terms of endomorphisms?
And I mean, not that I could. That's why I was looking for a name, so I don't really know. I wish I knew, but I
But should I think of z hat as being roughly like the Adams operation, but not when it's getting something fun?
I would love that to be, yeah, probably. Let me say I would love that and probably, but I don't know for sure.
So here the S1 is the pointed S1 or the unpointed?
But here it's just a space, right? So you're computing a mapping space and it's just a space.
Mapping spectrum or mapping?
No, mapping space. Sorry, I should save my notation maybe. Well, okay. I guess I'm going against normal usage, but because I used capital M so far, let me just.
Capital M usually meant mapping spectrum or mapping space?
Well, I've used it to mean spectrum, and I've seen Lars shaking his head. I meant mapping spectrum. I should have meant. All right. Well, yeah.
Yeah, but you don't
Now
have,
what you mean?
Now I mean mapping space.
He means the opposite of Lurie.
I mean the opposite of Lurie. Maybe it's not.
you don't have mapping spectra for algebra.
There's no mapping spectrum for algebras. If I have two algebra maps, I can't sum them.
Ah, okay, so you have only mapping space. Only this one is defined. Yes, and this is a simplicial. It is a space without base point.
Yeah, but it's just what would be the base point, right? I mean, I don't know.
No, but there is a tensor structure already, and THH you said so. There is already an identity.
There's the identity. The identity is the base point 0 here. Is in the copy? I mean, the component of the identity here is the component indexed by 0, and there's a base point in S1, I guess, corresponding to the identity. If you, yeah.
But the core product is really disjoint.
It's a disjoint union. This is a disjoint union, not a disjoint. Okay. Okay. Now in the remaining 15 minutes, so let me mention that. Okay, I want to move on to these two things. I'll say a few brief words about this one before I move on to this one. So for the k-linear version, you can sort of just deduce everything from the absolute version using well, either a definition or a formula. That k-linear HH is just, or is, let's say K is going to be now a commutative ring spectrum, but you can think of an ordinary commutative ring, e.g. ordinary commutative ring. And yeah, okay, tensor THH K with THH twiddle. What is THH twiddle? THH twiddle is now a functor from k-linear categories. Into spectra, and it's basically the not into spectra, into THH of K modules, and it's the canonical THH of K linear structure on just the forgetful functor that goes like this. Okay, so this functor has a canonical THH of K linear structure, and that's the one I'm considering here.
Which functor is a canonical? This.
So okay, so you have maybe a forgetful functor here, UK. You have and this composite has a canonical THH of K linear structure, and this one is what I call THH twiddle. And you can use this to compute various variants of this one. It's relatively straightforward once you have the correct guess. So namely, as a functor on k-linear categories and with values in spectra, what you find is THH of k-linear maps from K to itself plus an S1. And if you're thinking, but of course you should consider that a K module, why wouldn't you?
Sorry, what are you computing right now?
The endomorphisms of HH of K. But you might think, okay, well, of course you get a THH here. You did spectra. You're stupid. Well, if you do this with values in K modules instead, sorry, you're not out of trouble because you still get maps of K, THH of K bimodules from K to itself with the brackets S1. So even if you're interested only in K-linear HH, so let's say K is FP maybe a perfect FP algebra more generally, and you still pick up this THH of K factor here. Of course, in the case of a perfect FP algebra, this guy is completely understood, and so you can actually understand this pretty easily. But you still have these extra operations coming from this THH of K.
So what does that look like, the first one?
Yes, the first one, so it's going to look like, let's see, no, sorry, K plus threefold loop space of K, brackets S1. The point being that, so if K is a perfect FP algebra, the point being that in this case, K is in this case,
Perfect usual algebra or simple.
yeah, usual, yeah. In this case, you have a cofiber sequence like this, which allows you to just compute. Yeah.
Where that degree 3 class I can think of as the thing that relates THH to HH.
Yes. And so this is the Bookstein generator. US. Right. And this calculation you can sort of straightforwardly deduce from this formula and the previous ones. It's not very difficult once you have these tools. And again, just as for THH, you can also sort of take tensor powers of this in various meanings, and you can also look at commutative algebra maps, but the answer becomes a bit uglier, I guess. But you can still at least in principle compute this. Okay, the last thing I want to say is I want to talk about this last variant, which is maybe the most difficult one. And this is where these low-day operations should come from, because low-day operations are not defined on arbitrary E1 ring or on assistive rings. They're only defined on commutative rings. And one question you could ask is, okay, low-day has these operations. They're useful to produce filtrations and maybe, understand the THH better. So are there other operations that we could use? Right, and as I said, there's a variant with operands. And so the point here is that if you just look at it with values in spectra, the THH from symmetric monadal categories down to spectra, sorry. This time it is literally just precomposing with the forgetful functor. And so by some basic adjunction nonsense, you kind of reduce to computing the following thing. So you reduce to computing the following thing, and now just on categories and no longer on commutative algebras, from THH to THH precomposed with the free functor. Free. And the free functor has a formula. The free functor, so at least when you forget back, you get a very nice formula that you're used to from classical algebra, which also holds in the setting. I just have to replace orbits by homology orbits. And now you're left with computing THH of that direct sum. And this, I don't know if this has ever been considered before, so I, again, don't know who to attribute this to, but at least the way I know how to prove it uses work with my co-authors on a previous project. So Carmeli, Nelson, and Yanofsky. You prove a more general formula, but in particular, this formula implies the following. That if you want to compute these THH of these orbits, you get the sum indexed by conjugacy classes of permutations. Let me give it a name, sigma, of tensor powers of THH, where the number of tensor factors is the number of cycle types in THH, or sorry, of cycles in sigma, modded out by the centralizer of the permutation sigma. And the centralizer has a bit of a weird action on this thing, but it has an action. Yes, sorry, what am I writing? THH of C. Yes. Let me give you two extreme examples of this action so you can see what these look like. Examples. If sigma is a trivial permutation, there is n different cycles in sigma. And the centralizer is the whole of sigma n. And so this is just the usual thing that you'd expect. THH of C tensored n times orbits. This is something like the free algebra on THH. I mean, it's one of the factors of the free algebra on THH. But the other extreme examples is if sigma is a cycle of length n itself, and there's only one cycle, and the centralizer is itself, so you have some kind of Cn action. And in this case, the Cn action is induced from the S1 action on THH. So Cn and S1, and you get THH of C or HCN. Right. So now you're trying to compute maps from THH into this big direct sum. And I told you earlier, at least for localizing invariants, but it also works for these kinds of functors that aren't quite localizing invariants. Into a big direct sum, but this formula involves a limit. And so you're trying to commute a limit in a direct sum. That's complicated. Luckily, this limit is very specific. And so, for example, rationally, you can completely answer that. So rationally, if you happen to care about this sort of stuff, kn locally for any n, I mean tn locally even for any n, you can actually, in those cases, you can actually swap the limit and the colimit. And you get that in those cases, so rationally or kn locally, Lattice shuffle operations are the only operations we have. So corollary, rationally over Q or Tn locally maps in this functor category from THH to itself is actually, well, some kind of direct sum. I'll write the sphere, but okay, let me write Q, but in the Tn local case, you have to Tn localize outside. And where the nth summon corresponds to the nth Lode operation, or the nth Lode shuffle operation.
And in Tn, you have implicitly a prime.
Yes, at any prime.
And the answer will be involving CP instead of Q.
No, instead of Q, what you put is you put the sphere here and you Tn localize outside. Let me write this. I should call this Kn. LTN of this direct sum. And the natural question is what happens integrally, because maybe that's the most interesting case. So integrally, what you can find is you can still create this map because you still have these summons. And you have a map which at every finite stage at least splits off. And you can ask, okay, is there a chance that this is everything, or is there a chance that this is not everything? And the point is, you have at least maps from THH into these that show up. And rationally or Tn locally, these aren't interesting, or I mean, yeah, they're interesting. But it turns out that integrally they can be very interesting. So let me point out an example. There's a map of degree -1. So for every prime p, there's a map of degree -1 like this to the orbits for CP. You can describe this map in two different ways. They're the same. You can either go with the with the cyclic Frobenius to the Tate construction and use the attaching map, or you can see this as the attaching map for the second, like the second truncated TR, so a typical TR or attaching map. For TR2. I mean, the same, okay? And in fact, you can compute more completely this mapping spectrum from here to here you can compute that this generates, I mean, this together with the natural thing that you'd expect generates everything. So let me finish with this. I don't know. This one. Maps from THH to THH lower HCP has one summand of this form, CP, that just corresponds to you naively putting out the orbits, and a summand corresponding to this operation in degree -1. So you have an omega. The S1 action acts freely, but because you're now in sort of p-typical TR, it turns out that the sphere you get here is a p-complete sphere. So I don't know the answer integrally, so I hope I can figure it out, because now it's a very concrete calculation. At the end of the day, it's no longer some kind of abstract mapping spectrum. You have an actual limit that you're trying to compute, which is how you get this sort of thing. But yeah, I don't know the answer yet. And yeah, I think I'll stop here. Thank you for your attention.
Other questions?
The last sentence, you wrote a proposition and then you said you don't know the answer. Answer to what?
I don't know the answer to this if you don't do it rationally or TN locally. Like if you just ask for this. So here, what I really mean is if you do maps from THH to THHQ, or maybe to THH TN localized. I forgot to write this. But if you just ask for literally this without any decorations, I don't know the answer. It involves stuff like this, but it involves other kinds of things, and also it involves swapping an inverse limit and a direct sum, or end up computing how this inverse limit compares to this direct sum.
Can you say how you compute that equality?
Which one?
The map tensor. No, yeah, this one.
Yes. So you write the same extension of scalars, restriction of scalars adjunction. So you reduce to THH to the S1 THH linear maps from THH to the S1 to THH. And now you observe simply that THH to the S1 is THH tensor sphere to the S1, and therefore this is like this term is also its scalar is it's also the scalar extension from spectra, and so you can restrict scalars as well, and then you just have to see what restricting scalars mean on this side, and it amounts to evaluating at the sphere, and it gives you a sphere.
Is there a way to characterize if you are given that map, which component in Z hat you are getting? And relatedly, this downstairs, if you're doing over FP, how is that related to Frobenius? As you say, it's somehow descent from FP bar over FP, so it should be related.
Yes, it's related to. I'm not. The point is, yeah, you can prove this abstractly by descent, and then I'm not sure how to actually. Yeah, that's what I was saying. I would like to know how to actually name this map. That would be very. So I don't really know. The answer to the question is I don't really know. I've asked a couple of people. It seems to sort of not be completely obvious, at least. But maybe there's a concrete way of writing it with the Frobenius. I don't know.
So is there a way to characterize? You are in somehow the identity component should be characterized by THH is always algebra over the input algebra, and somehow you require this map to be linear over that, or?
Yes. I mean,
It's only for commutative. What do we all think of commutative?
sorry, what?
THH is a factor on commutative.
No, this is THH as a functor on categories viewed as a symmetric monoid functor. But the inputs are not commutative algebras. The inputs are just maybe rings or categories.
The theory is like input.
This is where the input is a commutative algebra, and this is where I don't know the answer fully. I just know it locally.
You have a map from the right hand side without the LTN, just the S, S,
Yes, yeah, there's a map. Yeah, there's a map, and it's for every finite direct sum, it splits back. There's a retraction.
for every,
Whenever you go from K to some finite L,
yes,
there's going to be a retraction.
integrally.
Yes. But it's not, I also know that integrally it's not an equivalence. I don't know if it splits if the whole thing splits. I think so, but I'm not sure. But there's at least extra stuff coming from these. These contribute, this also splits off, for example.
Why this doesn't contribute when you truncate? When you
No, it does.
to LTN.
Yeah, that's sort of the miracle of this localization is that it's sort of because you've localized before. Of course, if I localized outside, it would keep contributing because this is a complete sphere, and I would just get QP.
Yes.
But because I've localized inside, it doesn't commute, and it turns out that localizing inside sort of cancels that contribution from the start. So the precise theorem that I'm using here is some kind of statement like here's a precise version maybe. If I take any rational spectrum and I look at this inverse system for any fixed D, I have an inverse system corresponding of these assembly maps for sigma n and omega n. This is sigma D linearly pro 0 is sigma D, equivalently pro 0. I'm phrasing it in this sort of weird way. In fact, in the case of, for D greater or equal to 2. In fact, in the rational case, it's just every map is 0. In the TN local case, you really want to say some kind of, you have some kind of uniform nilpotence, so maybe uniformly nilpotent. And this just fails integrally. This is not true. All the maps are 0 non-equivalently, but they're really non-zero equivalently. There's some kind of Euler maps.
And the tensor is before, what is the order of the operation?
I first loop my thing n times, tensor, and then deloop n times.
Okay.
So
it's not, okay.
I think the parentheses are.
No, because
right, sorry. And this is just not true if X is not rational or if you're not T and local. But if it is true if you're tensoring with, if you're rational or tensoring with some kind of finite type complex. It's a finite type n complex. And the uniformity is quite important to be able also to just really pull out this direct sum.
If X is a finite complex.
No, sorry. X is some rational spectrum here.
Okay.
And the point is that these maps are they're non-equivalently, they're null, but because you're rational, this implies that they're sigma D equivalently null. And so this allows you to swap everything with everything. You never have to worry about limits in the direct sum scope meaning, and you can actually get this. In particular, maybe one thing I want to point out is that over connective rings, this paper that I mentioned at the very beginning of Klimt, she finds that for rings you have actually a product instead of a direct sum because of some connectivity estimates. But these connectivity estimates just start failing for categories, and so you cannot you just get a direct sum. Kind of interesting.
Sure, maybe that's a premature question, but do you expect the answer integrally or want be at least to be the same if you consider maps compatible with either?
Can you say the question again?
The question was that, this is actually on algebras, it's a map into a filtered vectorized.
Yeah. I would think so.
And the question is what mentors?
Well, if you put, of course, if you put a commutative algebra here, then.
No, but the target is still just.
Yeah. So I don't know. Yeah.
What was the question?
The question was whether what will be the answer? Like,
If you replace the word spectrum by the word filtered spectra, where the filtration you put on THH is the even filtration.
Oh.
Because THH of a symmetrical model category is in particular ring, like a commutative ring spectrum that has an even filtration. You can decide to forget different amounts of structure, and one of the structures you can forget is just the monodal structure, but you can remember filtration. I guess you would have to sort of compute the even filtration on this kind of ring. So I guess it's accessible by the same methods. I don't know if yeah, the answer is the same. Oh.
So the even, okay.
Yeah, that's a good question. I'll add it to my list of things to figure out.
If there are no more questions, let's thanks, speaker again.